Hello everyone, welcome back. This is 1-11, Introduction to Timings in the Combat Redstone series. I'm MU222, so today I'm going to talk about certain timing methods, including component timings, observer double pulsing timings, and also piston plus component timings. So basically how pistons would push components and produce different timings. And finally, I would talk about closing or opening time calculation because I haven't included that into dashboard, but then it's important for you to know. So, yeah. And I'll also go through some useful resources for you, basically summarizing all of the things that I've discussed in this video. So without further ado, let's get started. Now, before I start this video, I want to have some remarks, I guess. Is that I'm not sure if any of you are aware of something called input bug. Don't worry, you don't have to know it now. You can always refer to 2-4. It will introduce right the first thing input bug. So, but then if you don't know input bug, then that's fine. If you know input bug, that's also fine. But then all you need to know is that we will always calculate timings based on repeater input. So either a repeater inputting or an observer. So anything other than direct inputting, like this. So yeah. And also, I will just ignore the effects of input bug. Not going to talk about input bug for this video. Although I do have one exercise that will showcase some effects of input bug for your understanding. And another thing is that I'll always use the term tick to refer to redstone tick, and game tick refers to game tick, of course. So yeah, unless otherwise specifying. So yeah, you will always hear me say 1 tick or 2 game tick, for example, because I need to cater both the players who use tick and game tick. So yeah, both kinds of players I have to cater for. So just bear with me. So yeah, so I'll just start with component timings. So let's know some basics first, because knowing some basic components would later help us understand some complex timings. So yeah, so let's learn about redstone dust. It has no delay. That's it. Do you think there's delay between this lever to this piston via this redstone dust? I don't see it. So yeah. Also, I'm using game speed mod because later it will be proven useful, and also it makes the piston look a bit nicer. But yes, although sometimes some representation of the game speed mod might be a bit inaccurate, so I will just change it back and forth. But yeah, anyways. So yeah, first thing we have to establish, no delay for redstone dust. So we can immediately use it here actually, because there's also no delay between here. Now, for a redstone torch, it has a 1 tick or 2 game tick delay. Now, the component timings part, actually throughout this section, are essentially a recap of what you have learned throughout my videos. So it will be including 1-1, 1-2, 2-2, if you have watched it or not, I don't know. So yeah, it will just cover these 3 videos, essentially. But then you don't have to watch 2-2 in order to understand. I will just recap all of the things. So yeah. Anyways, so this is the section from 1-1. So redstone torch, 1 tick or 2 game ticks. Similar for repeater, 1 tick or 2 game tick. But then there are also 3 other settings for repeater. So this will be 1 tick, 2 tick, 3 tick, 4 tick. But then if you are using game tick terms, 2 game tick, 4 game tick, 6 game tick, 8 game tick. And you can see it has a very nice animation. And you can also confirm that the redstone torch has the same delay as this repeater, because you can see this deactivates as this activates, and vice versa. So yeah, that's another property that I've introduced in 1-1. So next, we would discuss about comparator and observer. They both have 1 tick or 2 game tick delay, unlike the repeater having 4 settings, comparator only has 1 setting, and obviously observer. So yeah, both comparing in subtraction mode. both 1 tick or 2 game tick delay. No difference. But then, observer, besides on just saying that it has a 1 tick or 2 game tick delay, it is also important to know that it emits a 1 tick or 2 game tick pulse, and it also has a 1 tick or 2 game tick cooldown. That's the thing that I left out from 1-1. But then, now you know. So here it didn't really show the pulse length for observers, but then yeah, just to confirm that all of these will have the same delay. So basically, now just remember the cooldown property of observer. It will come in useful in one of the situations at the back. So yeah, now we move on to some which we call instant updaters. So we have node block, activator rail, empowered rails, these two, and yeah, instant updaters as stated in 1-2, and they also provide no delay when detected by an observer, so very similar to a redstone dust. Now I'm not going to activate this yet because there are also other things that is basically instant. So this is saying droppers, hoppers, dispensers. So yeah, all these three are also provide no delay when detected by an observer. So in conclusion, all of these pistons activate at the same time. That's basically it. We know that this redstone dust has no delay from what we established earlier, so all of these must also induce no delay. At least by themselves, not the observers. So yeah. Now, you heard me saying the dispenser, when detected by an observer, the dispenser induces no delay. Well, that's true, but then if you're detecting the dispense item, then it's a bit different, because it actually has a 2 tick or 4 game tick delay. So we see here, both of these activate at the same time. So yeah. And we can infer this from directly these two pistons are at the same time. So if we have this 2 tick repeater that compensates for this dispenser with the dispense item, then it must be a 2 tick or 4 game tick delay. So you can see throughout the video I will always use these pistons that powered either in sync or just a very marginal discrepancy apart. So you will see me do that a bit later. So this is one of the ways that can basically prove to you some complex timings based on simple component timings. So yeah. Now next would be redstone lamp. It's quite similar to dispenser, except on activation it acts very similar to any other instant updaters or all of these guys. So on activation, you see these two power at the same time. So dust, redstone lamp, no delay. Activation, no delay. The activation though, these two power at the same time. So there's a 2 tick or 4 game tick repeat here. So it must mean that this redstone lamp has a 2 tick or 4 game tick delay on the activation. So yeah, that's the property of redstone lamp. So next would be pressure plates. Pressure plates are a bit more complicated actually. So what you need to understand is that there are 2 types: stone wooden versus lighted and heavy weighted pressure plate. These are the 2 classes, let's just say. They're not really types, but anyways. Next thing is that if you recall your knowledge from pulse extenders, you will know that this is a 5 tick or 10 game tick pulse. This is a 10 tick or 20 game tick pulse. So yeah. Then we will analyze how these pistons fire and to determine the pulse length of these. So let's just fire it first. So you can see that these 2 has a 5 tick or 10 game tick. These 2 has 10 tick or 20 game tick by referring to these 2. But yeah. But then this isn't exactly the full picture. The full picture is that for stone and wooden, they will check if the entities are here every 10 redstone ticks or 20 game ticks. And if they're not here, obviously they will deactivate. And it's also similar to light and heavy weighted pressure plate, except they check every 5 ticks or 10 game ticks. So yeah. basically double the frequency of this. So yeah, basically that. And yeah, it's also important to say that it is check every some ticks or game ticks. So check every is a very important term because it does not imply the delay. It implies a clock that is constantly running when the pressure plate is activated, and it will just see for every moment when it needs to check. So basically, the pulse length would always be in the magnitudes of the checking frequency, essentially. So yeah. So now moving on from this kind of complex pressure plate thing. So we are also interested in looking at this dropper hopper monostable circuit because it also comes in very useful in some situations. Now, let's focus on the pulse length first. So, in case you don't know, this 3 tick would give a 3 tick pulse, this 4 tick will give a 4 tick pulse, and then the delay for this is the same as this. And then we only need to analyze the behaviors of these 3 pistons in order to determine the pulse length of this. So we just need to calibrate for the delay of this. So let's just see the pulse length. You see the activation is the same for all of these 3, but then the deactivation goes from the left to right. You can look at it again. So yeah. Okay. We know that this has a 3 tick or 6 game tick pulse. This has a 4 tick or 8 game tick pulse. But what would be the middle one then? It cannot be 6 game tick. It cannot be 8 game ticks. So we take the middle, 7 game ticks. Why is it 7 game ticks then? Not any other decimals, let's just say. Well, it's due to how the game process things. The game only process every single game tick. So every single component must activate or deactivate on an integer value of game tick. It can activate or deactivate on 0.5 magnitudes for redstone tick, but then it has to activate or deactivate on integer values of game ticks. So if it is between 6 game ticks and 8 game ticks, or 3 ticks and 4 ticks, then it must be 3.5 ticks or 7 game ticks then. So there you go. This dropper hopper monostable has a 7 game tick or 3.5 tick pulse. But then what if we add a minecart to it? This is a 4 tick pulse, so let's just see. Oh, both of these deactivate at the same time. Also they activate at the same time. So if you have a minecart here, it actually increases the pulse length by 1 game tick or 0.5 tick. So yeah, you can see the difference between adding a minecart or not. So now, besides on noticing the pulse length, it is also important for us to know the delay induced by the dropper hopper monostable. So we can just take a look at the delay here. We know that all of these pistons activate at the same time, as demonstrated just now. So what is the delay for these repeater and comparator? Well, 2 ticks or 4 game ticks. This repeater, well, 4 ticks or 8 game ticks. So what is the difference between these two and these? The answer is 2 ticks or 4 game ticks, which would be induced from this dropper hopper. Now this means that the comparator has a detection delay of 2 ticks or 4 game ticks. Because the item would be here, but then the comparator takes some time to realize, essentially. So, yeah, that's basically it. 2 tick or 4 game tick detection delay, we can say. The term might not be exactly accurate, but you get what I mean. So, yeah. Now, next, we will talk about something that you might have seen or not seen, because this is from 2-2. They talk about odd game tick components, so you might not have learned them yet, but then I'll just talk about how the timings matters here. just for your reference. So if we have a scaffolding block that has a block change, like this, like for example, we have an iron trapdoor below here, then it will change the scaffolding state, which will be detected by the observer. So yeah, observer is very powerful. Now let's just see how this powers. It's from left to right. This has 1 tick or 2 game tick delay. This has 2 tick or 4 game tick delay. So 2 game tick, 4 game tick. What would be this then if it's in between? So of course 3 game tick, because integer values of game ticks. And 3 game tick subtracting 2 game tick would be 1 game tick for this scaffolding. So this scaffolding adds 1 game tick of delay, or 0.5 ticks if you want to say in Redstone tick. So yeah, similar for this log. Well, we have a similar setup here. This glass pane must respond to this glass pane, and then 1 tick, 2 ticks, or 2 game ticks, 4 game ticks. We don't know this yet, so we will just test it. Oh, we see it's again at the middle, same as this one. So what does this mean? Well, we know that this is 2 game ticks when the block arrives here. This is 4 game ticks when the block arrives here. Then, since this has been in between, so it must be 3 game ticks. 3 game ticks minus 2 game ticks, 1 game tick for the leave. Now, just to make sure that this proof is accurate, we can also replace this leaf with a note block, because note block is basically the same as this. So it's not the piston that caused the 1 game tick delay. You can see these two power at the same time. It is the leaf that caused the 1 game tick delay. It's strictly the leaf. So you can always refer back to 2-2, half the components and their applications for more information. I don't like the title, actually, for now, because it should be odd game tick components. So, but yeah, the title is set, I cannot change it. So yeah, anyways. Last thing is something that I haven't included anywhere. So yeah, that is 1-1, and then we went to 1-2, I didn't mention it, and then we went to 2-2 here, but then this one I never mentioned it. So I will just introduce you here. So it's about hopper transfer rate. So if we have these 3 shovels that would just go into this hopper, then yeah, we can basically determine the timings for each item transferred. Since they must transfer at the same rate, you won't expect them to transfer at different rates. So we can just calibrate these pistons and to see how they would fire exactly, and they fire at the same time. So let's just explain why this happens. The first item goes here, so only this does power since this is subtracting 2. So this does powers, and then after 8 ticks or 16 game ticks it will power. The second item comes in, it will power up to this dust, and then it will power this 4 tick or 8 game tick repeater, and then finally this comes in and powers this, which would power this basically instantly. So to determine the transfer rate, well, we can just see the difference between this and this. If these two power at the same time, then the difference must be the 4 tick or 8 game ticks. So similar for this, so 4 tick or 8 game tick. If we want to see 2 items in between, so 8 ticks or 16 game ticks, but then we can just divide it by 2, so again 4 ticks or 8 game ticks. So yeah, it's very consistent. So yeah, that is the hopper transfer rate. At standard conditions, it can be slightly different at some very weird instances. I'm not going to cover those. Those are far too complex to be included here. So that's all for the component timings. I will move on to observer double pulsing timings. So we have the basic knowledge of component timings now, so we can start to analyze on some more complex circuits. For example, when observer gives 2 pulses. So let's just take a look at here. We have this circuit. This observer detecting a piston base. 2 observers here. or one observer in each. And then this has an extra 2 tick or 4 game tick delay. So let's just activate this and see what happens. Oh, this actually has 2 pulses. But look, these 2 power at the same time during the first pulse, and these 2 power at the same time during the second pulse. So what does this mean then? Well, first thing we need to notice is that this observer has 2 pulses, alright. The second thing is that what's the delay for the first pulse? Well, it's actually no delay, because thus piston, same time, 2 observers, same time, these 2 same time, so no delay here. But then what's the second pulse? So what's the delay between the first pulse and second pulse? That's the critical question to answer, which is 2 ticks or 4 game ticks, because that is the discrepancy. And we can see that these 2 power at the same time, so it must have this difference from this to this. So the 2 pulses have a 2 tick or 4 game tick interval. Or you can say it is 2 ticks or 4 game ticks apart for the 2 pulses. So if you want to completely count from this dust line, so this observer powers from 1 to 2 or 2 to 4 game ticks. This observer powers from 3 to 4 or 6 to 8 game ticks. And you can just infer to the middle that it powers both times. And since this powers at 1, this powers at 3, so you can see 2 ticks or 4 game ticks apart. And yeah. It's also very similar for this case, except we need a 2 tick pulse, and it's detecting a piston head. So same thing happens. We have this 1 tick again, this extra 2 observers, so representing this 2 tick repeater or 4 game tick repeater. So yeah, the same thing essentially happens. And yeah, also if you 2 tick this piston base, the same thing would happen. So yeah, I just didn't include it here, but then you can just try it yourselves. In fact, I can even just show you here. There you go. So yeah. Now, there's also some things that is important for you to know. First off, remember the observer cooldown. 1 tick or 2 game tick. So observer powers a 1 tick or 2 game tick pulse. Okay, so 1 tick is used, and then it has a 1 tick or 2 game tick cooldown. So another tick is used. So 2 ticks or 4 game tick for a complete cycle of activation and deactivation before it can power again. And essentially, this piston provides the minimum amounts of delay, because the 2 pulses are 2 ticks or 4 game ticks apart, which means after the cooldown, the observer immediately powers again. Immediately. So that is the minimum, essentially, and can only be achieved by using pistons, for example. And if you use other components, that's the second part, then it actually won't work. So say if we have a redstone lamp that's powered by a 0 tick pulse, recall that redstone lamp, it should activate instantly. It has no delay on activation, and it should have a 2 tick or 4 game tick delay on deactivation. So this should probably represent the 2 tick or 4 game tick apart difference for these 2 pulses, but then if we see it here, it doesn't really have. It only powers 1 pulse. Actually, you're already seeing that the 2 tick repeater case here is the same thing. So the observer should, let's just say should, have 2 updating instances for this observer, but then it doesn't. It doesn't really. Instead, it only has 1 pulse given. So yeah, only pistons can do the double pulsing, essentially. So yeah, that's basically the case that you need to remember. But then, yeah, the double pulse is useful. It can do, for example, double piston extender auto retraction things, but then sometimes you need the pulse length to be slightly longer. But then what would be the timings? So we would move on to a bit longer pulse this time instead of restricting ourselves on using pistons or using 1 tick or 2 ticks. So if we have a redstone lamp this time instead, so it's a 1 tick pulse instead of the 0 tick pulse here. So let's just see what will happen. Again, these two are at the same time. We just calibrate it if we need to test it without prior knowledge. So when will this lamp and this dust power same time? Okay, so these two observe at the same time, so that's why these two are at the same time. But then what about the second pulse then? What's the extra delay? Well, 2 ticks, 1 tick, 3 ticks, or 6 game ticks. The 6 game tick additional delay allows these two to power at the same time. So 3 ticks or 6 game ticks apart for a redstone lamp powered by a 1 tick pulse or 2 game tick pulse. And very similar here, we have a 3 tick this time instead of a 2 tick in previous this one, which will only have 1 pulse. But then what about a 3 tick pulse here? Then you will see again these two are at the same time. These two same time, these two same time. First pulse, second pulse. So again, let's just see. This starts firing this node block, same time. Observer, repeater, same delay, so same time. Very usual. But then what's the delay between this and this then? Well, 3 ticks or 6 game ticks. Since these two, same delay. The 3 ticks or 6 game tick is to accommodate for the difference between this and this. And we can see from here. So yeah, the 3 tick or 6 game tick apart in delay. So you can also just confirm that these two cases are equivalent if we have these two repeaters on different timings, like so. Now, what if we just increase the pulse length 1 more tick? Actually, it's quite similar. For this, we just replace this observer with a 2 tick pulse. 2 tick repeater, what am I saying? So yeah, same thing. So again, dust, lamp, same time. Observer, observer, same time. But then what's the difference between this and this? 4 ticks or 8 game ticks because of these 2 tick repeaters or 4 game tick repeaters on this piston. So yeah. So you can see it's 4 ticks or 8 game ticks apart. So same for this one. A 4 tick pulse this time. Dust, no block, same time. Observer, repeater, same time. And then the extra delay between this and this 4 tick repeater or 8 game tick repeater. So again, same time. Nice. And you can also conclude that these two are the same. Like so. So yeah, you can see that starting from 3 tick pulse or 6 game tick pulse, if we just add in the pulse length, then it will just differ by the same amount of pulse length for this repeater, for example. And for the redstone lamp case, you just reduce it by 2 ticks because we already established that redstone lamp deactivates 2 ticks later. So yeah, that's basically the case. So that's all for the observer double pulsing timings. I'm sure you can just infer some useful information from these examples. I'm not going to show you all of them because it's impossible, but then yeah, you can just infer some useful patterns for your understanding. I'll also include more information in the resources below. So we will finally move on and talk about piston and plus component timings, which is basically just describing how pistons interact with components by pushing them and cause different timing behaviors. So yeah, but before we can understand piston plus component timings, we need to know 2 basic principles first. The first one is that a sticky piston or a piston extends a block in 1 tick or 2 game tick when receiving at least a 1.5 tick or 3 game tick pulse. So here as an example, we have repeater which represents 1 tick or 2 game tick. This, we don't know the delay yet. These two have the same delay, so let's just see if they are at the same time. Oh, they do. So what can we conclude? For this case, then we can see that this has a 1 tick or 2 game tick delay induced to this node block. Same for retraction actually, so we ignore the extension this time. So 2 observers here, 2 observers here, same timing, okay? Now this redstone torch, 1 tick or 2 game tick delay, this sticky piston retracting a redstone block, we don't know the delay yet, but then we can see by retraction, oh, they power at the same time. So 1 tick delay or 2 game tick delay must correspond to this sticky piston retracting the redstone block as the same timing. So 1 tick or 2 game tick delay. So yeah, and it's also similar to a normal piston extending block. So if you replace this with a normal piston, it actually behaves the same. So it doesn't have to be a sticky piston, but then only sticky pistons can retract blocks. So that's the difference. But yeah. Okay. Now, after knowing that pistons extend blocks in 1 tick or 2 game tick of delay, we need to introduce something quite quirky, which is what we call piston activation delay. Now, I think that my definition of piston activation delay is a bit more broad than others, but then I don't really care about the namings for this one because it's still essentially the same concept, let's just say. But then yeah, I just named 2 cases as piston activation delay. But then yeah, let me explain. So the first case is what everyone agrees, is that piston activation delay refers to the 1 game tick delay or 0.5 tick delay of pistons being powered by a block that is extended by another piston. So that's the first case. And the extended must be by a pulse with duration greater than or equal to 1.5 tick or 3 game tick pulse. That's the first case. That's the standard definition of piston activation delay. So we can see here, for example, we have previously established that this is a 1 tick or 2 game tick delay to this node block here. So same for this here. So this will have a 1 tick or 2 game tick discrepancy due to 1 observer and 2 observers. But for piston, is it 1 tick or 2 game tick delay? We are not sure. Let's just power it. Neither. It powers in the middle of these two. So these observers, we can reduce them. Then when does this piston power? We say 2 game tick here or 1 tick, 4 game tick here or 2 tick. So 2 game tick, 4 game tick. What's the one in the middle? 3 game ticks. So the piston has a 3 game tick delay when this piston fires. So how does this 3 game tick come from? Well, piston extends block in 2 game ticks or 1 tick, but the 1 game tick activation delay to pistons is the thing that causes this piston to react 1 game tick later than this one, causing this piston to extend in the middle of these two. That's why. Similar for retraction actually. Same thing. You can see is in the middle. Okay. Here comes the second part of piston activation delay, which not everyone agrees that it should be used this name, but I don't really care. So piston activation delay also refers, by my definition, the 1 game tick delay of blocks that can be extended or retracted again by another piston. So blocks including normal pistons, sticky pistons, any blocks, to be honest. As long as they are being extended or retracted. Alright. So let's just consider this situation here. So when can this sticky piston retract this normal piston? Well, if we try 2 tick, yeah, it will work. 2 tick or 4 game tick will work, but then what about 1 tick or 2 game tick? It doesn't. What about 3 game ticks then? We haven't tried 3 game ticks. Let's verify why this is 3 game ticks first, okay? This piston retracts this redstone block. Well, it powers the dust at 2 game ticks. But then the 1 game tick activation delay from the first case induces on this piston. So this piston can only push away this redstone block after 3 game ticks. And what does this piston do when it has a 3 game tick delay? It retracts the piston. Oh, so nice. So yeah. So what does this setup show? Oops. What does this setup show? Pistons, well, they retract in 2 game ticks or 1 tick, but then it still needs an additional 1 game tick in order to be retracted by another piston. So yeah, that's why we need the 3 game tick delay. So there you go. That's why this setup 3 game tick works, but then 2 game tick doesn't work, even though piston retracts in 2 game ticks. So yeah. So now that we have the concepts of piston extending or retracting in 2 game ticks or 1 tick, and the concept of piston activation delay, we can finally explain some pistons extending, for example, observers or redstone blocks, and determining the timings of it. Right. So the first case is that when a sticky piston extends an observer and is being powered by a 1 tick or 2 game tick pulse, so that's the first case, or the second case, at least a 2 tick or 4 game tick pulse, then the observer pushed will power after 2 ticks or 4 game ticks. Does it make sense? It actually does, because we recall that pistons extend blocks in 1 tick or 2 game tick. So after extension, the observer would have a delay and power after another 1 tick or 2 game tick. So adding together 2 tick or 4 game tick. So makes sense. So we can just prove it from here. So this is 2 tick definitely. And this node block and this piston, do they power at the same time? Yes. It's not like we have a piston pushing a block or retracting a block that powers these 2 components. We are just powering from the observer, so there isn't any piston activation delay. So that's the thing that you have to be aware. So we know that this is a 2 tick delay or 4 game tick delay, but then we might not know this delay, but don't worry, we can just test it. And they power at the same time. So this proves that this indeed induces a 2 tick or 4 game tick delay to this piston, since it has to be the same delay as this, right? So yeah. And also this case is actually similar to a normal piston pushing an observer. But then the normal piston pushing an observer has less restriction than the sticky piston. Recall that the sticky piston has to be pulsed by a 1 tick or 2 game tick pulse, or at least a 2 tick or 4 game tick pulse. But the normal piston, it can be pulsed with any pulse length. It doesn't even matter. So yeah, you can just test it yourselves. And quite similarly, on the retraction of an observer, what will happen then? Well, the observer, again, powers after 2 ticks or 4 game ticks from the retraction instant. So yeah. Also, throughout the remaining of this video, we will assume there are no instant retraction methods. That's why that's an assumption that we need to assume here. Because if this observer would instantly retract, then the timings will be different. So we assume there are no instant retraction methods. So, okay, we will always assume normal retractions. So we are considering when exactly the retraction instant is. So do we consider the redstone torch here? Not really. We don't care about the delay of the redstone torch. We only care about when this piston starts to retract. So there's 2 ticks of delay or 4 game ticks of delay here. So 1 tick, 2 ticks, or 4 game ticks from the repeater observer. So we might not know the delay of this setup here, but then we see they power at the same time, so this must mean that this 2 tick or 4 game tick is represented exactly from this setup here. So there you go, 2 tick or 4 game tick delay from the retraction instance. Also, just one additional requirement is that the retraction of the observer must not face in the same direction as the sticky piston. And if it cannot face in the same direction as the piston, then we obviously have some special cases when the piston and the observer faces the same direction. So that's what we are going to discuss next. So what happens when a sticky piston retracts an observer that faces in the same direction? Well, we need to define it case by case, mainly on the pulse length again. So if it retracts, so say if a sticky piston retracts an observer with a 1 tick or 2 game tick pulse, also no block event delay. Block event delay is explained again in 2-4. So we don't have block event delay in this setup. So it actually emits a 0 tick pulse, which can be received by components other than pistons or sticky pistons. Does it make sense? Actually, yeah, it does, because this is 1 tick or 2 game tick. This powers after 1 tick or 2 game tick, but then by the time it can power the 1 tick or 2 game tick pulse, it would be retracted by the sticky piston. But then the 0 tick pulse still goes through. So let's just see. The lamp powers, but not the piston. So this basically proves the point. The components other than pistons will power, not the pistons. You can just try with any other components and see if this is true. I can tell you it's true. So yeah, basically that. Now, so that's basically the case that you have to consider. And there are also other cases that might be useful, but I'm not going to introduce it here. I'm going to introduce it in the resources. So you can just check those out if you want to, because I quite frankly cannot cover all of them. It would just take me too long. So yeah. Now we would move on to redstone blocks instead of observers now. Alright. So let's talk about extending a redstone block first. And of course, we again have to define it by pulse length. So what happens when a sticky piston extends a redstone block with, let's just say, a 0 tick or 0.5 tick or 1 tick pulse? So this will be 0 to 2 game tick pulses. Then actually, the redstone block will power all components with the same delay as the pulse length received. What do I mean by that? Let's take a look at 3 examples, respectively 0 tick, 0.5 tick, and 1 tick. So 0 to 2 game tick, all going to be discussed. Here, this is a 0 tick pulse. Don't worry. You will learn this, I think, again in 2-4. 2-4 is quite useful, actually. But yeah, this is a 0 tick generator for pistons, unlike this one. This one can't even power it. So, okay. This dust line, it has a 1 tick repeater, 2 game tick repeater. Same delay as these 2 observers, right? So we are here to determine the delay induced by this piston to the and the redstone block to the node block and the piston. So what will happen then? Oh, all 3 pistons extend at the same time. So yeah. Now it might be weird that you don't have to consider piston activation delay, but that's simply because this redstone block is pushed into here, or is placed into here 0 ticks after this powers. Literally. So it is placed instantly to here. So that's why the piston activation delay does not apply in here. So if you recall the piston activation delay, it must be at least 1.5 tick or 3 game tick pulse. That's why I said like that. It's because of the scenarios here. And quite similar, the 1 game tick pulse case, so this is a 1 game tick generator for pistons. So yeah, what will happen then? This is 2 game ticks. This is 4 game ticks. So 1 tick, 2 ticks. This we don't know. Let's just see. Oh, this powers first, then these two, then this. Now, what is the delay between this and this? Well, 2 game ticks. Then if these 2 pistons are going to power in between this 2 game tick interval, then it must be this adding 1 game tick, because integer game tick values. So what does this mean? This has a 2 game tick delay, then this has a 3 game tick delay. 3 game tick minus 2 game ticks, 1 game tick. So this piston and the rest of the block induces 1 game tick to both the node block and the piston. Like so. So if it's a 0 tick pulse, it adds 0 tick of delay. It is a 1 game tick pulse, it adds 1 game tick of delay. It's also similar if it's a 2 game tick pulse or 1 tick pulse. So 1 tick or 2 game ticks, 2 tick or 4 game ticks. We are here to determine this sticky piston to redstone block. They power at the same time. So what does this mean? The additional observer represents the delay of the sticky piston to this redstone block to the node block or the non-piston. So this is 1 tick or 2 game tick of delay. So yeah. So you can see that it's dependent on the pulse length given to the sticky piston. That extends the redstone block. Alright. But then, what happens when the sticky piston, instead of extending at a very short pulse length, 0 to 1 tick or 0 to 2 game tick, what happens if it extends with at least a 1.5 tick or 3 game tick pulse? Well, we are going to use piston activation delay now. So you can probably know the result of this. So this is 2 game tick of delay. This is 4 game tick of delay or 2 ticks of delay. 3 tick or 6 game tick. These 2 observers, 1 tick or 2 game tick. We should know these delay, but let's just say we don't know. What will happen then? Did you see it? Let's slow it down. These 2 power, then this middle right powers, then the right one powers. Alright, so what does this mean? These 2 have the same delay, so this has a 1 tick delay to here. It reconciles with what we have discussed in the past, right? Pistons extend blocks in 1 tick or 2 game tick of delay. Then this 2 pistons and this piston has 2 game tick interval, and this falls in between, so it must have 1 game tick of delay from this 2 pistons. So 3 game ticks of delay for this here, and 3 game ticks minus 2 game tick here. The 1 game tick piston activation delay from this piston. See? So yeah, I should say in the full picture, this is 4 game ticks, and this will be a 5 game tick. And then 5 game tick minus 2 game ticks, 3 game ticks. 3 game ticks minus 2 game tick of piston extension, that will be the 1 game tick piston activation delay. Fully explained. It makes sense. And it also makes sense for when the pistons retract the rest of blocks. Same thing, same order, same timings, essentially. So yeah. So you can just see how the knowledge combines into explaining these piston plus component timings. And hopefully you will understand a bit more about these timings, and we will move on to also related to timings, but then this is closing or opening time calculation. Because it's sometimes important for us to know when doors open and when doors close, if we are doing fast doors. Although this series focuses on compact doors, it's still important for you to know how fast doors close and how fast doors open. Now, we introduce a term called normal time. So normal time has two variations, the normal closing time and the normal opening time, of course. So let's just say what normal closing time is. So it basically refers to the in-game time period during which the door blocks are moved into the inside of the hallway or tunnel and into the position of the door frame upon activating the input. So similar for opening, except it just moves out the door blocks, of course. So yeah. This is taken from the regulations documents of the Resident Squids records catalog. So if you want to know a detailed discussion, you can just find it on 2-9 terminologies and 3-1 complete terminologies and competitive redstone practices. 3-1 I haven't uploaded yet, but then yeah, it'll be on its way. Now, just by hearing normal closing time, the official definition sounds very wordy, and you might not even know what it means. Well, let me rephrase it. It is the duration of the door animation, considering only the door blocks. So we don't even consider the hallway blocks. This means that the input delay and reset time are not considered. So what is input delay? Input delay is the delay between you activating the input and when the first block starts to extend or retract in the door. And what is the reset time? Well, after the door closes or opens, reset time would be referring to the time in which you cannot touch the input, but only after the contraption is fully reset. So the time between the door fully closes and opens and you can open or close the door again, that is the reset time. So yeah, the input delay and reset time are not considered during the normal closing or normal opening time. Basically that. And yeah, we are only interested in the normal time only. Other times, we don't really care. So from this, that we do not consider input delay and reset time, we can include a useful formula now, or we can derive a useful formula, which is the normal time equals the end time of door block animation subtracted by the start time of the door block animation. Makes sense, right? The end time minus the start time, that will be the duration of the door functioning, or at least the door block animation time. So yeah. Now, I would say that determining the start time of door block animation is trivial, but then is the end time of the door block animation trivial? No, it isn't. In fact, determining this has several counting methods, and it will actually yield different results. This arises due to what we have learned before, piston activation delay, and piston extension and retraction time, and also the interpretation discrepancies on when exactly the door is closed or open, which I will just explain when I actually went on to that. So yeah, again, we assume there are no instant retraction methods because that would just break some of our assumptions when counting the time. Although to modify it is also quite simple, it's not really that hard. But then I'm not going to test you on this or let you exactly know. You can figure it out yourselves. So let's talk about opening and end time, because opening is actually easier than closing, I can tell you. So if the last door block starts to be retracted at time equals capital T, then the first rule tells us that the opening end time would be capital T plus 1.5 tick or 3 game ticks. This is known as the plus 0.15 second rule, because 1.5 tick or 3 game tick essentially equals 0.15 seconds if there's no lag and 20 TPS. So yeah, So let's consider this piston here, and from this block. When is the start time? Let's just consider this block as the start time. Okay. Then after 4 ticks or 8 game ticks, this will start to retract. Alright? And then this is capital T, because this starts to retract. So 4 ticks or 8 game ticks, capital T. And then we add 1.5 ticks or 3 game ticks to it. So 4 ticks plus 1.5 ticks, 5.5 ticks. Or 8 game ticks plus 3 game ticks, 11 game ticks. So 5.5 ticks or 11 game ticks. That's the opening end time. Right? So, but then, if I said there is a 0.15 second rule, guess what? There should be another rule. Introducing the plus 0.1 second rule, which basically instead of capital T plus 1.5 ticks or 3 game ticks, it will be capital T plus 1 tick or 2 game ticks. Let's consider this again. So what is the end time? Now, consider from this block. Capital T, still the same, 4 ticks or 8 game ticks, but then we add 1 tick or 2 game tick. That basically means the opening end time is now 5 ticks or 10 game ticks. So yeah, you can see this yields different results, and which will be the perfect time for me to explain why the 0.15 second and 0.1 second rule even exists. 0.1 second rule exists because of piston extending and retracting at 2 game ticks. So obviously we should calculate based on this information and fact. But then others would argue, what about the piston activation delay? I mean, yeah, sure, you can calculate based on when exactly the block is retracted, but then you still have the 1 game tick piston activation delay before you can open or close the door again. So we should consider that. And hence the 0.15 second rule is the alternative to the 0.1 second rule. The history isn't exactly this, but then the arguments for 0.15 second rule versus 0.1 second rule is this. So yeah. And also I can tell you that I'm more for the 0.15 second rule. And yeah. So throughout the series, I will just use the 0.15 second rule. And also in the exercises, if I ever going to ask you the questions on piston retracting, it will also be plus 0.15 second rule. So yeah, you can use 0.1 second rule, but then make sure that your answers are 0.15 second rule based. So yeah. So, okay, we learned the opening end time and also learned some history, let's just say, or reasons on the rules. We can now learn the closing end time. Yes, closing end time is slightly more complicated. So, again, we have capital T, which is that the last door block starts to be extended at time equals capital T. And if the last block is extended with a 0 to 1 tick or 0 to 2 game tick pulse, then we would consider the pulse length, which we denote as capital P. And the closing end time of the door block animation is capital T plus capital P. Alright, let's look at 3 cases. The 0 tick case, the 1 game tick case, and the 2 game tick case. So 0 tick case, let's count from this block, okay? So this is 2 tick of delay, or 4 game ticks of delay. And this is capital T. 2 ticks or 4 game ticks. What is capital P then? It's a 0 tick, so a 0 tick or 0 game tick. 4 plus 0 or 2 plus 0 which will be 2 ticks or 4 game ticks from this block. So yeah, it is no longer dependent on the 0.15 second or 0.1 second rule. We only consider the pulse length. So this is consistent. So how about the 1 game tick case? Let's consider from this piston. What is the delay from this piston to this piston then? 2 game tick plus 1 game tick activation delay. 3 game ticks or 1.5 ticks. Okay? That's capital T. 3 game ticks. What is capital P then? This is a 1 game tick pulse to this piston. So 1 game tick. 3 game tick plus 1 game tick. What's that? 4 game ticks or 2 ticks. So 2 ticks. Finally, the 1 tick pulse case or 2 game tick pulse case. Let's count from literally this piston. I don't care. So capital T is 0 tick or 0 game tick. What is the pulse length P? Capital P. That's 1 tick or 2 game tick. 0 plus 1 or 0 plus 2. So the result is 1 tick or 2 game tick. So yeah, 1 tick or 2 game tick. Alright. This explains the closing end time for the 0 to 1 tick or 0 to 2 game tick pulse case for the last block. What happens if the pulse length is just slightly longer or a lot longer? Now, this would be the case for essentially a 1.5 tick or 3 game tick pulse case, although it's a bit more complex. But yeah, in case we cannot apply these conditions, then we apply the 0.15 second or the 0.1 second rule again. So we would disregard the pulse length, capital P. We only consider the 0.15 second case or the 0.1 second case. So let's just consider this again, using the 0.15 second rule. From this block, what is capital T? 4 ticks or 8 game ticks. Then we add 1.5 ticks or 3 game ticks. What would that be then? 5.56 or 11 game ticks for this tick then. That's the closing end time. What about the 0.1 second rule? Capital T, still 4 ticks or 8 game ticks. 0.1 second rule. 1 tick or 2 game tick, we add to that. So 5 ticks or 10 game ticks. So yeah. So that's how you calculate the closing end time. You can see it's based on the opening end time, but then with the additional exception for 0 to 1 tick or 0 to 2 game tick pulse. See. Now, a final remark for you is that if you have a piston with a 0 to 1 tick pulse or 0 to 2 game tick pulse, but then pushing another block in front, then you cannot say this is the last block anymore. The block in front is the last block. Why? Well, let's just see. I will change to this. This is more accurate. Look at this case. So, you can see the back block actually goes to here basically instantly, but then the front block still takes time for it to actually arrive to this position. You can see it's pushing to this position. What does this mean then? This means that the time needed for this block to go into this position is longer than this block going to this position. So this block cannot be counted as the final block. So yeah, we have to not care about this block and not care about capital P, and we only apply the plus 0.15 second rule or the plus 0.1 second rule. So similar to all of the cases here actually. So this here you can see again the back block is actually slightly faster than the front block. Now for this case, actually you cannot really see. Now I'm using pulse at end, which is the default in your vanilla settings. So you can see there isn't any difference actually. But then if you use the no pulse, then you see there's a slight difference. You can see the front block is extended slightly slower. So that is the purpose of the game speed mode. And also this basically explains the 0.15 second rule and the 0.1 second rule, essentially. 0.15 second rule essentially is represented by the no pulse case here. Although this isn't the actual case in vanilla, but then it just makes the animations a bit nicer. It's more of an aesthetics mod, you can say. However, I already explained the reasons why we use the 0.15 second rule and the 0.1 second rule. 0.1 second rule being pistons extend retract blocks at 2 game ticks. That's it. But then the 0.15 second rule is that, hey, you should also include the piston activation delay. That's it. That's the reason why. So yeah, I'm not going to go in depth into the arguments, but then what I'm going to go in depth is, again, some bit of history, let's just say, before I end this with introducing the resources and the exercises. So a recap of history. In versions 1.8 or below, we apply the plus 0 second rule instead of the 2 rules I've introduced you. And that's because of the behaviors in 1.8 or before of moving piston or block 36. But then from 1.9, they basically change moving block. And this causes us to consider 0.15 second rule and 0.1 second rule instead, because of its technical changes. I'm not going to go in detail of what it exactly is. So yeah. Alright, that's all I need to say. So I'll just introduce you the resources that I have in the document. So just refer to the document because I cannot show it here. So the first one is summarizing the component timings that I have at the very front. So you can see the component I have redstone dust, torch, repeater, comparator, observer, node blocks, and so on and so on. And then there are 2 extra columns. One is the activation delay, one is the deactivation delay or pulse length. So yeah, it's probably quite straightforward for the activation and deactivation delay. But then how do you know if it's deactivation delay or pulse length? Well, the pulse length only has 2 cases, which is the drop-off moment unstable with or without cards. So those would be the pulse length, because I don't want to make another column, quite frankly. So yeah, it's probably quite trivial for you to study this table, but then the later tables might not be. It's going to be increasing in complexity. So the second table will be summarizing the double pulsing timings. So you'll see the components, redstone lamp, piston base, piston head, and other components, and also the pulsing received. And you will see the start of first pulse will be always the same, 1 tick or 2 game tick. But the start of second pulse is dependent on the pulse length received, of course. So if you see a high event, this means that it's not applicable. So there's only 1 pulse. But then if you see there is content, so for example, pulse length plus 3 tick or 6 game tick, or 2 tick or 4 game tick, blah blah blah, then you can see that there is a second pulse. So yeah. And the third and fourth table, they are essentially the same, but then they are only describing on different components. So the third table describes what happens on components other than pistons, but the fourth table describes the effects on pistons. So yeah, third table components other than pistons, fourth table on pistons, and also some additional information. So yeah, the main thing I just need to say is that you see the pulse length received bracket and position. So if you see something like 0 to 1 tick or 0 to 2 game tick, and then brackets retracted or brackets extended, then what does that mean? If it's bracket retracted, this means that the block is initially at its retracted position. So the pulse would spit out the block to its extended position. So vice versa for extended. So it's initially at the extended position. So the pulse length would retract the block instead. So yeah, that's basically what it means. So if you still cannot get what it means for the tables, you can just ask me in the comments or just direct message me if you want to. So I will just get on to the exercises now. So this is on input bug. So there are some questions that will guide you on understanding more about input bug. You can obviously just check out 2-4 if you want to study input bug, but then doing this exercise makes you discover by yourself what input bug actually is. So yeah, that's basic that. And then this one is asking you to explain why these double piston extenders don't work. You can reset them by using the circuits on top. This one is asking you on the closing and opening time. Yeah. So yeah, just recall the knowledge there. And also I intentionally use circuits that you cannot deduce any timings from this. So I would like you to use some tricks from what I have used here, is that if you see the pistons, they retract or extend in sync, then that will be the timing. So you can use this right circuit here for your reference, essentially. This one is just to ask you to calculate the timings and just explain why this works. This one is also on timings, and ask you which of these would work and why they work or why they don't. You know, always reset it from these on top. And then the final sub question would be asking what combinations of dust and observer on these blocks would work. So there are 8 combinations, just list them out all. And you would know the pattern if you know fully the pattern from these. So yeah. And finally, this last exercise is literally taken from 1-2, exercise 2.8. So yeah, that I said you need knowledge from 1-11 and even 2-4, but then actually 1-11 has sufficient information for you to answer this question already. So yeah, just good luck on that. And yeah, so that's it for me. Again, the work download, the solution, and the documents will be in the description below. So just check them out if you want to. And yeah, thanks for watching, and I will see you in the next video.